We don't really do much. It's so nice.
I know, like, I
Uh,
don't know what he wants us to do.
Yeah.
Like, when we're like, so you want us to do this, like,
Oh, this is
grams?
LED.
Yeah, that sounds good.
I don't know. Okay.
Huh? Yeah, this is Pat, oh my God, so it's Shirley. Shirley.
I really like, he's canceled that like 3 times, just for shits. Just like,
Yeah,
he's like, how'd you guys like the day off? It's like,
and it's
"Cool,
always the
Friday."
Friday one,
Otherwise-
which is nice.
The other one,
Do you have to,
and this.
We gotta inoculate and then wait for it to grow and then.
Source that is doesn't light, but it requires its own magnets and power supply and everything. It's very inconvenient. Very inconvenient to us. But we have a nice prism here. Looking for that's nice. Let's try this one.
You got everything you needed?
Yes, yes,
Okay.
thank you.
Perfect.
Whatever.
Yeah, please, let's see. Yeah, well, that's LED light. That's LED light. It doesn't do. It's not. So LEDs are monochromatic, but the white LEDs have several different colors. They mix them up. And after that, there is the fluorescence. So it is not the best source, but still. Okay. This. Okay, so what matters in this in the following chapter, the difficult part, well, it is not difficult, but the part that you have to really pay attention is sign convention for different distances in geometric optics. And last time we said that the focal length for convex mirror is a positive number for a mirror that looks like this. And it is a negative number for a mirror that looks like this, or concave convex mirror. In a similar manner, if the image is formed behind the mirror, you're going to have DI negative. And if it is formed in front of the mirror, it is a positive number. What other problem? Oh, yes. So the size of the image is a positive number if it is upright, and it is a negative number if it is inverted. So this, when DI is negative, in other words, when the image is behind the mirror, it is also virtual, always virtual in that case. And those are the rules of the game. And last time we said that if you observe if you observe those sign conventions, there are only two formulas that solve all calculational problems in this and in the following chapter also. The first one is the mirror equation, 1 over dO plus 1 over di is 1 over f. And the second equation says that magnification, linear magnification, defined as the ratio of image size to object size, is the same thing as di divided by dO, but you have a minus sign in front of that, which should be forgotten. Also keep in mind that sometimes you need to use the fact that, well, let's write it this way. The focal length of a mirror is half of the radius of the spherical surface. So you need also to be able to form images. And to form images, you need at least two, to be able to trace at least two light rays. And we actually defined 4 easy to trace light rays. So if you have, let's say, a concave mirror, always start with the principal axis. And the easy to trace light rays are a light ray that comes in parallel to the principal axis, is going to be reflected through the focal point. In other words, it is going to go this way. So this is one easy to trace light ray. Another light ray that is easy to trace would be a light ray that comes in to the focal point. How is it going to get reflected? Parallel to the principal axis, of course. And the third one, so this is ray number 2. The third one would be, let's say, a light ray that comes to the center, let's say, is going to be reflected back exactly the same way. And you have a light ray that is going to hit the center of the mirror, it is going to go at the same angle. But those 3 easy to trace light rays are sufficient. In a similar manner, you can form images in a convex mirror. So a convex mirror is like this. Here again, always start with the principal axis, but now the center of the mirror is behind the mirror and the focal point also is behind the mirror. For convex mirrors, the focal length is a negative number. You have to insert it by hand. And let's say how to form images. Well, using a similar procedure. Just keep in mind that now, instead of working with real light rays, you have to also work with their continuations. So let's say that you have an object that is located right somewhere here. The first light ray that comes in parallel to the principal axis is going to look like this. How is it going to be reflected? It has to be reflected in such a way that here is the focal point. It has to be reflected in such a way that its continuation goes to the focal point. Another easy to trace light ray would be a light ray that goes, let's say, to the center of the mirror, maybe like this. Well, of course, it cannot go through the mirror, but its continuation is this way, and the reflected light ray is right here. Where is the image formed? The image is formed by the continuations of those reflected light rays. In other words, the image is going to be right here. And the properties of the image are, well, first, is it real or virtual image? It is behind the mirror, so it is virtual. It is upright, and it is reduced in size. So, no matter where you place the object, if the mirror is convex mirror, image is always virtual and always reduced in size, which you can verify by playing around with different locations for the object. So knowing those things, and especially keeping in mind the algebraic sign convention for different distances, we can answer problems similar to problem number 7 and problem number 8. Yeah.
In a convex mirror, is it always going to be upright, or what would be the scenario where it's inverted?
Okay, let's investigate if for convex mirror you can have inverted image. Probably one way to investigate would be to get a convex mirror and just play around with it. But since I don't have a mirror like this, I'm going to use animation. And you can have this animation on the internet, the website you're going to see easily. Okay, so let's look at this animation as much as we can. Here is the object. Is pencil okay, or we can use a different object? Okay, pencil, let's leave it as pencil. So here is the object, and here is the image. So for this particular location, they have used, well, let's show the focal points. So we to see what exactly we use. So here is the focal point. The center of the mirror should be somewhere here. And now look, a light ray that comes in parallel is going to go, its continuation goes to the focal point. So this is our light ray number 1. And they used, well, they used the light ray that I don't want to talk about, but they used light ray number 4 from our previous class. Light ray that comes in, hits the center, is reflected at the same angle it came from. So its continuation is here. So here is the pencil. It is virtual, right? It is virtual and upright, as you see. Yeah.
Can you email them
The link?
Yeah.
Okay, I'll email the link, but you can also see it. Can you just to find the link, make a search using PHET. Make a search, PHET, and there you're going to find multiple simulations in biology, chemistry, physics, and everything. You go to physics and you select only geometric optics. And this is the only simulation that is present. Okay, now let's start changing the location of this object and see if the image is going to invert. Does it invert? So convex mirrors are simple. They're always virtual images, always upright, and always reduced in size, which you can actually get pretty without much trying to remember it. Because look, convex mirror has diverging reflected rays just because of its shape. If the rays diverge, they can never intersect. Only their continuations are going to intersect. Therefore, there is no other way but to have the image behind the mirror and therefore virtual. Also, a mirror that is convex, diverging, it kind of reflects the entire world. The world is a big place. You don't have other option but to have a smaller image in order to fit the entire world. And the uprightness, well, I don't have a word explanation why it is always upright, but it is. Okay, any remarks and issues? So it's a good simulation to play with, even though it is kind of, I would prefer, well, feel free to play with the simulation if you feel like, but I would urge you to do image formation with pencil and paper. Okay. So remarks and questions? If not, let's do the homework questions. I guess that most of you have finished this homework assignment. Again, the tricky part of that assignment is realizing that sign convention is something that you cannot skip. So problem number 7 is for concave mirror. This means positive focal length. And they say that you use this mirror to as a projector, basically. And they say that you have a slide that is located at some distance from the mirror, clearly in front of the mirror, and so on. The setup is similarly shown on the figure. How far from the wall the mirror has to be located. Well, look, you are going to form the image. And in order this image to be sharp, that image has to be on the wall, on the place where you are projecting, on the screen. And look, in this problem, they tell you that, well, they give you the radius of the mirror, therefore they give you the focal length. So they say the focal length for my version is half of 56 is 28 centimeters. And they say that the distance between the object, which is the slide, and the mirror is 34 centimeters. In other words, they say DO is 34, positive 34 centimeters. It's in front of the mirror. how far the wall should be. In other words, part A, they're asking what is the DI. And you say that 1 over DI is equal to 1 over F minus 1 over DO. In other words, you have 1 divided by 28 minus 1 divided by 34 is going to give you DI. And therefore, DI itself is equal to 1 divided by 28 minus 1 divided by 34 inverted. And when you do this arithmetic, you're going to get, well, hopefully the correct answer. Notice that the correct answer is going to be DI is going to be a positive number, which means that the image is going to be in front of the mirror, and therefore it is going to be real rather than virtual, and therefore you can see it. Part B, they say that in part B of this problem, they say that the height of the object HO is given 1.3 centimeters. They want you to figure out the height of the image. And of course, you say, you know that HI divided by HO is equal to negative DI divided by DO. You already have the value of DI. HO is given, so you just have to do the multiplication, and you shouldn't forget this negative algebraic sign. So you're going to get, for HI, you're going to get a negative number. Right? You're going to get, it is negative HO times DI divided by DO. And you have to keep this algebraic sign, this negative algebraic sign. This negative algebraic sign says, what about the image? Inverted, upside down, inverted image. This is what it says. So how, well, this answers part C, right? You have to, your object has to be upside down so you to see it upright. But any remarks? Yes.
So you should always include the sign. It's not like magnitudes and.
Well, there are problems where they may ask about magnitudes, but in geometric optics, algebraic signs tell you that something. So, yeah, you always have to keep track of the algebraic sign in geometric optics. Okay, other remarks? Should we do the next problem, or you already know how to do it? Well, the next problem is not that different either. It is, yeah.
Can you explain again what's the difference between O and I, HO and HI? It's between DO and DI.
So one of the two equations in the following chapter, and we derived those equations. One of the equations is the mirror equation, this one, and the second equation is this equation. Well, you can say it is two equations or three equations, but the second or third equation tells you that the ratio of heights is negative the ratio of distances. And this is what we use in part B of problem 7. Okay. So problem 8, again, is quite similar problem. Let's see what does it say. You have convex mirror. What does it say? Convex mirror means that the focal length is a negative number. So they say that the radius of this mirror is 62, which means that the focal length is 31 centimeters with negative algebraic sign, according to our sign convention. They say that the image is behind the mirror, 19 centimeters behind. What does it say? This means that DI is negative 19 centimeters. Again, the sign convention forces us to insert a negative algebraic sign, because when the image is formed behind, it is a negative distance. And knowing this, you can figure out, part A, you can figure out, part A, the location of the object. So DO, you can figure out directly, right? You have that 1 over DO is going to be 1 over F minus 1 over DI. In other words, in our case, it is going to be 1 divided by 31 with negative algebraic sign. And after that, you have minus 1 divided by minus 19. In other words, you have 1 divided by 19 minus 1 divided by 31. Right? Minus with minus, and I'm writing this first because it's positive. In other words, DO itself is going to be equal to 1 divided by 19 minus 1 divided by 31 inverted. Right? And when you plug in the numbers, you're going to get some positive DO, which means, of course, that the object is placed in front of the mirror, as it should. So all convex mirrors create upright image. And you can verify that by looking at the algebraic sign of HI. So if HO, we said you place your object always in front, upright. So if you look at the algebraic sign, for example, of part B, let's do magnification, part B. Magnification, M, defined as the ratio of HI divided by HO, but it is also equal to negative DI divided by DO. So we established that DI is a negative number. With this minus sign, it is going to give you a positive number. DO is positive, and therefore magnification is positive number, which indicates upright orientation. Or you can say that HI is equal to negative HO DI divided by DO. So we established HO is positive because you keep your object upright. DI is negative, DO is positive. The resulting expression has a positive algebraic value, and positive HI indicates upright position of the image. Is it, what is the object, smaller or larger? Well, when you calculate this magnification, you're going to get a number that is smaller than 1, which means that you're going to have reduced in size object. Okay. Yes.
So just to clarify, when HI isn't given to understand inversion or if it's upright, we can solve for HI basically if we've got DI and DO to understand inversion.
That's correct. So look, even if HO was not known, let's say you didn't calculate HO, or it is not even given, right? It is not even given. You always place your object upright. So HO is always positive number. And therefore, from this expression, you can deduce the algebraic sign of HI. And if this algebraic sign happens to be plus, this means that your image is upright. If the algebraic sign of HI is negative, it is inverted. In our case, it is going to be always a positive algebraic sign for HI, and therefore always upright image.
You're saying it's always positive because it's a convex mirror.
Yes, yes. Convex mirror, always. You don't need to remember rules, like always, if it is convex, it always has to be upright. You just have to follow the logic. But, well, remember, it doesn't hurt. The problem is that once the semester is over, everything that you remember is going to be forgotten. And this is the rule. The more you learn, the more you forget. The more you forget, less you know. Therefore, more you learn, less you know. Doesn't it work that way? I don't know.
It's incredibly disappointing.
Right. So what is the point of going to school, right? Okay, now. So we have a few minutes. Do you have any remarks, questions, any comments? So we can see some conceptual questions related with reflection. Let's quickly do some conceptual questions, and after that, we're going to talk about refraction of light. Okay. So here the questions are about flat mirror, but well, they're still useful and interesting questions. So go ahead and see what you can figure out for this. What do you say? You have option either 1 or 2 or 3 or 4. Anybody? Okay, let's look at this. We're going to see the object. So again, you're going to see the object at point 2. So look, your brain always assumes that the light ray that enters the eye came from a straight line rather than from some reflection. Right? And this is why you are going to perceive the object to be located not at point one, but at the continuation of the reflected light ray. So as you are going to see also in the next chapter, when we talk about the human eye in one of the next chapters, you look with your eyes, but you see with your brain. Okay.
So when it says perceived, like, maybe I don't understand. If I see light coming from a mirror straight at me, I don't think that that light's coming from the opposite side of the mirror.
Well, I guess you do. It's not getting, like, your mind perceives that's going through the mirror, it's not getting reflected. Because it says light travels from straight.
Or you can say that Dane's brain works in a different way. That also may be the case.
I kind of think of it like, if you have like a comb on the bathroom counter, like, you know, the comb's on the counter in front of the mirror, but if you're looking through the mirror, you're gonna see the comb on the other side, like behind the mirror, on the counter still. So that's where you're perceiving it, is the image on the mirror is like straight. Does that make sense?
Yeah.
We'll see.
Okay, look, so you can think that we're training people here to look at the mirror in the morning, right? Here, especially this one here. They actually have given you the answer just by giving you the right diagram. So they have shown you the light rays that are going to give you the image of your feet and the image of your head, the top of your head, So what do you say? How big mirror do you need in order to see yourself in all of your glory?
Is it talking in this exact instance or any instance? Because technically any size, it just matters how close you are to it, right?
That's supposed to be. So if you're further away, it could be tinier and you could see your whole stuff.
Well, you know that's not exactly the case for a flat mirror, right? Experiment tomorrow morning in front of the mirror, and well, look.
I guess it probably is implying that you're seeing only your whole self, nothing outside of your height.
Yeah, nothing outside. Yes. So, what is the minimum size of the mirror that you need? Look, this diagram tells you. So you need to see this distance is what? Half of 150 is 75 centimeters. So you need 75 centimeters from here to here. And after that, you need half of those 10 centimeters to see your forehead and hair. In other words, you need 75 plus 5. $80 centimeters is what you need if your height is 160. Right. This is what is the. Oops. So in other words, those height size mirrors are overkill. You don't actually need to have full, yeah.
But like in this instance, like you kind of tell by tracing the line from like her eyes to her feet, you know, and then like that where it hits the mirror is like the lowest point of the mirror, right? Where that's point B. But if she were to take like a step back, that line would be flatter. So wouldn't it like, would it still go through point B?
But in that case, you're going to need, you're still going to look, if you get, yeah, if you get here, you're still going to have a similar construction, geometrical construction. Just draw it yourself. You cannot. I understand people here are looking for bargaining. You want a smaller mirror. No, it's not going to work. You need. You cannot beat it. You cannot get a better bargain. What do you say? Let's see. Let's see. So they're saying how far back of the big mirror. So look, the first mirror is going to create the image right here at 2 meters from the big mirror. And the big mirror is going to create the image on the other side, 2 meters. So it should be 2 meters, right? Let's see. Okay, so let's go to the next chapter, and next time we can continue with conceptual questions. So look, imagine that you have the interface of 2 different transparent media. Transparent, both of them transparent. Let's say the interface is right here. And this is medium 1, and this is medium 2. And let's say that you have incoming light rays this way. So again, both of the materials are transparent. What is going to happen? You're going to have, from the original light intensity, some of the light is going to be reflected according to the law of reflection. But since both materials are transparent, some of the intensity of the incoming light is going to be in the second, entering the second medium, and you're going to see a second light ray. This is the light ray that we call refracted light ray. So you always, when you have interface of 2 materials, if both of them are transparent, you're always going to have, in addition to the reflected light ray, you're always going to have a refracted light ray. Since we already studied reflection, very often we're just going to forget the reflected light ray because we already know about it. We know everything that is to know about. Now, notice that the refracted light ray doesn't continue along a straight line. It is bended. And while doing some experiments and doing some reasoning, you can verify that the amount of bending and also the direction of bending of the refracted light ray depends upon the speed of light in the second and in the first medium. The speed of light in different media is usually different. So instead of working with the speed of light in some material, traditionally we work with a number called index of refraction. Index of refraction N is defined as the ratio of the speed of light in vacuum to the speed of light in this particular material. The index of refraction is a number that is always larger or equal to 1. Because the speed of light in any medium is either close or smaller than the speed of light in vacuum. So for example, the index of refraction of air is almost exactly equal to 1, because the speed of propagation of light in air is almost exactly equal to the speed of light in vacuum. Now, if the index of refraction of the first medium is N1 and the index of refraction of the second medium is N2, you can figure out the angle at which the refracted light ray is going to bend. Remember that in optics, all angles are with respect to the normal to the surface. So if the incident angle is θ1 right here, and the refracted angle is θ2, the angle of refraction θ2, again, notice with respect to the normal to the surface. You can prove, and the proof is not given in the textbook, so I'm not going to prove it, but it is easy to figure out that the two angles, θ1 and θ2, and the two indices of refraction are connected with the following formula. N1 times sine of θ1 is the same as N2 times sine of θ2. So this formula is known as Snell's law, and it allows you to calculate the angle of refraction if you know the indices of refraction for the two media and the incident angle. So one result of this Snell's law is that if the light ray enters optically slower material, if the second medium here, the speed of light is lower. In other words, lower speed of light means higher index of refraction compared with the index of refraction of the first medium. The bending is going to be always in direction to the normal. So bending is going to be this way, as shown on this diagram. In the other case, when the refracted light propagates in optically faster medium. So now N1, but N2 is smaller than N1. The light moves faster in the second medium. Again, here is the incident light ray. The refracted light ray is going to bend in this direction. Therefore, the index, the angle of refraction theta 2 is going to be larger than the angle of refraction theta 1. So this is one typical conceptual question that occurs in different tests. They give you either the speed of light in the medium, 1 and 2, or they give you the index of refraction for each of the media. And they're asking which way it is going to bend, or the other way around. They give you the direction of the bending, and they're asking where is the light going to be faster, in the first or in the second medium. So how much time? We have 1 more minute. Okay, let's see a refracted light ray. Well, we have the setup right here. Here it is. Okay, so maybe let's look at. So you see, let's turn off some of the lights. So it's pretty well visible, right? Notice that the light ray here that came in, let's say, or let's look at the single light ray maybe. Notice that you have a refraction from the first surface. You have another refraction from the second surface. The incoming and the outgoing light ray are parallel to each other, but they are shifted. They are shifted. Well, if your observer located right here, you're going to see the image. Your eye is automatically going to continue this. And therefore, the image that you're going to see is going to be shifted. The real is here, but the world that you see is going to be here. So when you are looking through the window of your room, you're seeing the world shifted a little bit because, well, the thickness of your of the glass of your window is probably smaller, so the shifting is smaller. But again, the world is shifted when you look through the window. So we're going to continue with refraction, dispersion of light, lenses on Friday. Don't forget the homework assignment. And see you on Friday.